All right, so problem 677. In 677, it describes a typical titration that's used to determine how much sulphite there is in wine. All right? And the chemical that they use to do the titration is I3 minus. Okay? And the amount of I3 minus is equivalent to the amount of iodine in solution. All right? So you can read through that problem there. It says sulfites are used worldwide in the wine industry as antioxidant and antimicrobial agents. However, sulfites have also been identified as causing certain allergic reactions suffered by asthmatics, and the FDA mandates that if it's more than 10 parts per million, you report it. The analysis of sulfites in wine uses the Ripper method, in which a standard iodine solution prepared by the reaction of iodate and iodide ions is used to titrate a sample of the wine. The iodine is formed in the reaction. The iodine is held in the solution by adding excess I minus, which combines with I2 to give I3 minus. In the titration, the sulfite is converted to SO2 by acidification, and the reaction during the titration is between the SO2 and the I3 minus. All right? Starch is added to the wine sample to detect the endpoint, which is signaled by the formation of a dark blue color. So, in a certain analysis, 0.0421 grams of sodium iodate. All right, so we have our grams of sodium iodate. We have our mass of sodium iodate in 1 mole. So now we're in moles of sodium iodate. And for every 1 mole of sodium iodate, you see in that for every 1 mole of sodium iodate, you get 1 mole of I3 ion, I3 minus, okay? And this is, they diluted that into 100 milliliters, it says. So this is the molarity of the I3 minus ion, all right? And then it says it required 0.00247 liters of that stock solution that was made. All right? And the stock solution's concentration was 0.00638 moles for every liter. Okay, so that's how many liters were required. This is how many moles per liter of the I3 minus ion there are. Okay? So, a 50 milliliter sample required, again, 0.00247 milliliters. What's the molarity of the iodine in the standard solution? That's this one here. How many grams of SO2 minus were in the wine sample? Well, for every 1 mole of this I2, let's see. Where did we get this 3 moles of that for every 1 mole of that? Oh yeah, that's from the top equation, sorry. So for every 1 mole of this stuff, this I3 minus, this represents I3 minus. As many moles of iodine there are, that's how many moles of I3 minus you can have. So this represents the moles of I3 minus. And for every 1 mole of I3 minus that's consumed, that was 1 mole of SO2. All right? So it's 1 mole of I3 minus for every 1 mole of SO2. Okay? How many grams of SO2? Well, for every 1 mole of SO2, how many grams of SO2 are there? So it's 16, 16, 32, 32, and 32 is 64. So there should be about 64 grams of SO2 per mole of SO2. So we've got 0.00247 times 0.00638 times 64. So it looks like 0.00101 grams of SO2. And the next question is, how many, or if the density of the wine is 0.96 grams per milliliter, what's the percentage of SO2 in the wine? All right. So this was 50 milliliters of the wine sample. All right. So we'll check this one before I erase it. but I'm going to erase that one. So the 677A, 6.38 times 10 to the minus 3 molar. Okay, so we got that one. So now I'm going to erase this one on the bottom so we can do part C here. In part C, we need to identify how many grams of sample there were. There were 50 milliliters of sample, and we want to know how many grams, and the density was 0.96 grams for every 1 milliliter. All right, so 50 times 0.96, and that'll be the mass of the sample. All right, so there's 48 grams in the sample size, and this is how many grams were SO2. So we have 0.00101 divided by our 48 times 100, so that's 0.002%. All right. Parts per million, that's part C. Let's double check these before we move on. 677, 1.1 times 10 to the minus 3, or 1.01, and then 2 times 10 to the minus 3, 2.1? Oh yeah, sorry, this is a 2.0021%. Okay, so then we're going to try to convert this to parts per million. You can do that up here. Okay, parts per million, part D, parts per million is calculated in a manner similar to percent, which is equivalent to parts per 100. Parts per million, grams of component per grams of sample times 10 to the 6th. What is the concentration of sulphite in the wine expressed as parts per million SO2? Expressed as parts per million SO2. Yeah, so what is the concentration? Okay, parts per million sulfur dioxide, basically. All right, so this value here, grams of component over grams of sample, which is this value divided by 100, right? And then we multiply it by 10 to the 6th. And we get 21.04 parts per million. Okay, so that's number 67. Pretty high parts per million sulfite or sulfur dioxide. All right, 679. A sample of copper ore with a mass of 0.4225 grams, that's the mass of the sample, was dissolved in acid. A solution of potassium iodide was added, which caused the reaction where 2 copper ions are consumed by 5 iodide ions. The I3- ion that formed reacted quantitatively with exactly 29.96 milliliters of 0.02100 molar sodium thiosulfate, according to the following equation. So 2 moles of thiosulfate were required for every 1 mole of I3-. What was the percentage by mass of the copper in the ore? All right, so it required 29.96 milliliters, which is the same as 0.02996 liters of the 0.021 moles per liter, and that's moles of the thiosulfate, S2O3 2-. All right, so that's how many moles of S2O3 2- it required, according to the following equation. And so for every 2 moles of S2O3 2-, there were 5 moles of I3-. Correct? That's what we see in, oh wait, no. There was just 1 mole of I3-. And for every 1 mole of I3 minus, there was 2 moles of copper. All right. So for every 2 moles of copper, or for every mole of copper, that is 63.55 grams of copper. And we want grams percent, grams of copper over grams of sample. Right? Because we want, like it says here, what is the percentage by mass of copper in the ore. So the sample was 0.4225. All right, so we have 0.4225, and that's grams of sample. So if we take this value, we have to multiply it by 100 to make it the percent. So we have 0.02996 times 0.021 divided by 2 times 2 times 63.55 divided by 0.4225 times 100. So I'm looking at 9.46% copper. 679, 9.463% copper, that's right. What else do they want to know? If the ore contained copper carbonate, what was the percent by mass of the copper carbonate in the ore? All right, so if we just add on right here, if we say for every mole of copper, there is 1 copper carbonate, right? And then we have to add one more little slice here. And for every 1 mole of copper carbonate, and we have to know the grams of copper carbonate per mole of copper carbonate, right? So we need to identify the molar mass of copper carbonate. All right, so copper 2 carbonate. $123.555. All right, so it's this value here is 123.55 grams per mole of copper carbonate. So if we take 0.02996 times 0.021 divided by 2 times 2 times 123.55 divided by 0.4225 times 100, and I'm getting 18.40%. Yeah. All right, good. Okay, so 681. Hydrogen peroxide solution can be purchased in a drugstore. A sample of such a solution weighing 1 gram was acidified with sulfuric acid and titrated with 0.02 molar potassium permanganate. The ionic equation for the reaction is as follows. Titration required 17.6 milliliters of potassium permanganate. 0.0176 liters of the potassium permanganate solution And for every 1 liter of the potassium permanganate solution, there's 0.02 moles. And this is the MnO4 minus. And for every, how many moles of MnO4 minus? For every 2 moles of MnO4 minus, there were 5 moles of hydrogen peroxide. All right, thanks to that balanced equation there. How many grams of hydrogen peroxide would this be? Well, this is moles of hydrogen peroxide. And for every 1 mole of hydrogen peroxide, there are 16, 16, 32, 33, 34, 34 grams of H2O2. So this should tell us how many grams of hydrogen peroxide there were in the initial sample. 0.0176 times 0.02 times 5 divided by 2 times 34. 0.0299 grams of hydrogen peroxide. What's the percentage by mass of the hydrogen peroxide in the original antiseptic solution? A sample of such solution weighing 1 gram. So they're asking for the percentage by mass. So we had 1 gram. So if this is divided by 1 gram, multiply it by 100, that's going to be 2.99%. All right, so 681. Good. 683. A sample of chromium containing alloy weighing 3.45 grams was dissolved in acid. All the chromium in the sample was oxidized to the chromate ion. It was then found that 3.18 grams of sodium sulphite was required to reduce the chromate to dichromate. Or no, let's see, perchromate to chromate, sorry, in a solution, with the sulphite being oxidized to sulfate. Write a balanced equation for the reaction of CrO4 2- with SO3 2- in basic solution. Yeah, CrO4 2-. Is that right? Where are we at? 83. CrO4 2- and SO3 2-. And this is going to CrO2- and SO4 2-. Is that right? Products are CrO2- and SO4 2-. Write the balanced equation for the reaction of CrO4 2- with SO3 2-. And it's in basic conditions. Basic conditions. Okay, so we'll take CrO4 2- going to CrO2. Okay, that's a minus there. So we need 2 waters over here. 4 hydrogens over on the left. And we have a net charge over here of +4 and a -2, +2, and this is a -1. So we need 3 electrons here to get to that -1. Okay, so we have 3 electrons. Now the other half reaction, SO3 2- going to SO4 2-. 1 water over here, proton over here. In terms of electrons, we need 1 electron over here. Let's see, the charge on the sulfur, making sure that this is right. The charge on the sulfur here is -2, -6, +4. 1's here, -2, -8, +6. So that can't be right, 1 electron. Did I make a mistake there? 4 minus SO3 minus 2 minus 6, so it has to be a plus 4, minus 8 minus 6, so there has to be 2 electrons. Oh, here's the problem. 2 protons, so there's 2 electrons. Alright, so we had 1 water, and that's 2 protons over here. So we need 2 electrons on the right. Okay. So we're going to have to multiply this one by 3, and this one by 2. I'll put the 2 and 3 over there so you can see it better from your angle. 6 electrons, 8 protons. Alright? So I'm going to leave out the electrons. We have 8 protons plus 2 CrO4 2 minus plus 3 waters plus 3 SO3 2 minus yields 2 CrO2 minus 4 waters 3 SO4 2 minus 6 H pluses. So we have 8 H pluses over here, so that's going to go to 2, and these 6 are going to be erased. 4 waters and 3 waters, so we're left with 1 water on the right. We're in acidic conditions, now we need to go to basic conditions. We need to add 2 OH minus on the left and 2 OH minus on the right. These 2 OHs combine to form 2 H2Os, right? With the 2 protons there. And the result is that this is removed. Okay. Alright. That should be the balanced equation, right? The balanced equation. Let's verify that before we go any further. 2, 3, water, 2, 2, 3. Okay, so that's the balanced equation. 683. How many grams of chromium were in the alloy sample? Okay. So it took 3.18 grams of sodium sulphite. So if we start with 3.18 grams of Na2SO3, we need to know we need to find the molar mass of sodium sulphite. Okay, so we can convert this to moles. So we need to know how many grams of Na2SO3 there are in 1 mole of Na2SO3. And then for every 1 mole of Na2SO3, molar mass of sodium sulphite. For every 1 mole, or for every mole of Na2SO3, that's 1 mole of sulphite. And we see up here, here's our equation, that there, for every 3 moles of sulphite, there were 2 moles of CrO4 2 minus. Okay, so here's the 126.043. All right. What other information do we have? How many grams of chromium were in the alloy sample? Well, for every 2 CrO4 2 minuses, for every mole of the CrO4 2 minus, there's 2 CRs, right? So for every mole of this stuff, there's 2 chromiums. And for every 1 chromium, how many grams of chromium is that? Well, chromium, each mole weighs 52. So that's 52 grams of chromium. So that would tell us how many grams of chromium were in the alloy. All right? So if we take 3.18 divided by 126.043 times 2 divided by 3 times 2 times 52. And this tells us how many grams, 1.75 grams of chromium. And we can divide that by the sample, which was what? .450. And I'm getting 50.7%. 50.70%. All right, 383. 0.875 grams of chromium in the original alloy. So we got the wrong value there. Let's see what we did wrong. Did I get this wrong? Sodium sulfite. Double check here the mass of the sodium sulfite. No, that's right. So double check what they're asking here. Write a balanced equation. We did that. How many grams of chromium were in the alloy sample? So this is how many grams of sodium. It was found that 3.18 grams of sodium sulfite was required to reduce the chromium. All right. So if that's how many grams we had, this tells us how many moles we had. And for every 3 moles of that stuff, we would consume 2 moles of this stuff. And for every 1 mole of this stuff, we would consume 2 moles of this stuff. Oh, this isn't right. For every 1 mole of chromium 4, there's only 1 mole of chromium because there's only 1 Cr in one of those. So it should be this number divided by 2. Both of those numbers divided by 2. So 1.749 divided by 2, 0.874, and 25%, yeah. All right. So what I had done, and I don't know why, but I thought that this was Cr2O4 or something. So for every 1 mole of Cr04, there's just 1 mole of chromium. Okay? So that's it. And for every 1 mole of chromium, each one weighs 52 grams. All right, 83. 85. Calcium chloride and sodium chloride are used to melt ice on the snow. A certain company was making a mixture of these 2 compounds for this purpose. A chemist wanted to analyze the mixture, dissolved 2.463 grams of it in water, and precipitated the calcium oxalate by adding sodium oxalate. The calcium oxalate was carefully filtered from the solution, dissolved in sulfuric acid, and titrated with KMnO4 solution, 0.1 molar. The reaction that occurs was as following. Titration required 21.62 milliliters of potassium permanganate solution. Going on to 85 here. All right. Going on to 85. Both the calcium chloride solution melt. Let's see. Chemist working on a sample that dissolved sulfuric acid and titrated with 0.1 molar. The reaction is recorded. 21.62 milliliters. Or that many liters, right? This is how many liters of solution. The concentration of the solution for every 1 liter, there's 0.1 moles of MnO4. 1 liter, 0.1 moles of MnO4 minus. All right, and for every 2 moles of MnO4 minus, there were 5 carboxylic acids. All right, so we have for every 2 MnO4 minus 5 C2O4s. Is that what they are? 2 minus. And same as, I could have put this as the H2C2O4 2 minus and then said that there was 1 of those for every 1 of those, but that's all right. Same thing, right? It doesn't matter because this is what we're after, how many of these there were. Because, well, that's the first question, how many moles of the carboxylate were present in the calcium oxalate precipitate? And this will tell us right here, because we're in moles of stuff here. So they're not asking for grams first, they're just asking for moles. So that'll tell us the first question, 0.02162 times 0.1 times 5 divided by 2. 0.00538, this is 85. That's weird that... Did I type that in right? Oh no, I didn't. I put 0.2162, not 0.02162 times 0.1 times 5 divided by 2. All right, 0.0054. 405. All right, and that's the first one for 85A. How many grams of calcium chloride were in the original sample? Okay, so the solution contained what? What was the sample contained? Calcium chloride and sodium chloride are used to melt calcium chloride and sodium chloride. All right, a certain company was marketing a mixture of those two compounds for this purpose. A chemist, okay, hold on just a second. Let's go. Okay, so finish this one up here. This is how many moles of the carboxylate there are. 0.005405 moles of C2O42 minus. All right. So the question was, chemists wanting to analyze the mixture dissolved 2.463 grams of it and precipitated the calcium. All right, so for every calcium, the calcium oxalate was carefully filtered for the solution dissolved in sulfuric acid. All right, and for every calcium that there was, for every oxalate there was one calcium as well, right? Because calcium oxalates, the compound for calcium oxalate would be CaC2O4. So for every mole, for every 1 mole of C2O42 minus, there's 1 mole of calcium ion. All right? And the question is, how many grams of calcium chloride were in the original sample? Well, for every 1 mole of calcium, there was 1 mole of calcium chloride. And 1 mole of calcium chloride has a mass of what? Chloride, 35.45 times 2 plus calcium, 40.08. So 110.98 grams of calcium chloride for every mole of calcium chloride. Okay, so this will tell us how many grams of calcium chloride were in the original sample. 0.005405 1:1 times 110.98. So basically, for every mole of the calcium chloride or carboxylate there must have been a mole of calcium chloride. So that's 0.59985 grams of calcium chloride. Okay, and let's verify that. 85.59999, good. And the last part, what is the percentage of mass of calcium chloride in the sample? So I divide that by the total sampled mass, 2.463, and I get 24.35%. All right. Excellent.